Hello and welcome to this video where I'll describe how to solve any kind of separable ODE. And so a separable ODE is one that's in this form right here, g of y dy equals f of x dx. And all this means is that on the left side of the equation, you have everything involving one variable, and on the right side of the equation, you have everything involving another variable. So I'll show you what this looks like actually in practice with a couple of examples. So I'll go into one right here. So let's say we have a question that asks you to solve for y in dy dx equals x squared over y. Now immediately this isn't in the form that I just wrote up here, right? But actually we can get it into that form pretty easily. So first we're going to multiply both sides of the equation by dx. So that's going to leave us with a dy equals x squared over y dx. And then we'll multiply both sides of the equation by y. So this actually turns into y dy equals x squared dx, like that. And so now it's a little bit more obvious that this is separable, right? Everything involving y is on one side and everything involving x is on another. So all that's left to do is to actually integrate, because anytime you see a dy or a dx alone and at the end of a function, it's kind of a sure sign that you should integrate there. And so we can integrate just like that, which is of course legal because of the differentials at the end. And so now we just take these integrals and then we solve for y algebraically. So this will give us y squared over 2 equals x cubed over 3 plus c. And the constant of integration only appears once, because if we had written it in two places, one for each integral, we could have just subtracted maybe the left side's constant of integration from the right, said maybe c minus d, for example, and then we can just rename that constant to be, in this case, just c or whatever you want to name it. So that idea of renaming the constant of integration by sort of absorbing other constants is really prevalent in ODE. It's just a way of writing something a little bit nicer, right? So now we just multiply by 2, gives us y squared equals 2/3 x cubed plus 2c. And here I'll show you a little bit more about that renaming. So because c is a constant, we have no idea what it is. It's totally legal for us just to call it something else, right? So let's say rename 2c equals a new constant named c1. And again, we're only doing this because it's a little bit nicer to write c1 instead of c. And since we don't know what c or c1 is numerically, there's nothing wrong with renaming it. We could solve for the constants if we had an initial value problem, which means that we were given a set of values that this equation satisfies. But here it's just asking us to solve for y, so we have no information on the constant, so we'll just rename it. So y then equals plus or minus square root 2/3 x cubed plus c1. And so that's going to be our final answer. So we solve for y, and we got a pretty nice function here of x. And so this typically happens with a separable ODE, as in it's just honestly not that difficult to move forward, at least if you know the integration, right? Like the actual separable ODE itself typically isn't a big deal. It makes a lot of sense when you think about like what you're actually doing, because I know in ODEs sometimes, like for example with the integrating factor, it's not really clear why you use the integrating factor until maybe the end of the problem. But here, you know, you're just moving forward, doing each step as it makes sense. So that's kind of why I like these ODEs a lot, because they're more intuitive. Okay, but let's go into a different example here. So let's say we have an ODE that's dy dx plus y squared sine of x equals 0. You may notice here that this is nonlinear. Actually, the ODE above is also nonlinear, and that's because of the x squared. But a recurring theme throughout every separable ODE is that they're always first order. Any other order other than 1 is non-separable. So this only works with first order ODEs. Okay. So first things first, let's move y squared sine of x to the right side. dy dx equals negative y squared sine of x. Let's group the y's on one side and group the x's on another. So I'm going to divide by negative y squared and multiply by dx. So dy over dx times 1 over negative y squared equals sine of x. Then I'm just going to multiply by dx, which gives us dy over negative y squared equals sine of x dx. All right, as you can see, every y is on one side, every x is on the other, and we have some differentials here, which means integration. So let's integrate with respect to those variables. All right, so the integral of 1 over y squared, I'm going to take out the negative of the integral. So the integral of 1 over y squared, well, that's just going to be y to the negative 2 plus 1 over negative 2 plus 1. So this is going to be y to the negative 1 over negative 1, like that. Okay, so the integral of sine of x dx is just going to be negative cosine of x, making sure to not forget about the constant. All right, so now we just simplify and solve for y. So these negatives cancel, and we can rewrite y to the negative 1 as 1 over y, and that still equals negative cosine of x plus c. And so to solve for y here, we can just take 1 over the entire equation. So we can do 1 over y, which just equals 1, or which just equals y, pardon. And that equals 1 over the entire right side. So 1 over negative cosine of x plus c, like that. And so that is the final answer. All right, we'll just move on to another example right here. Just keep it going. So let's say we have x dy dx equals 1 minus y squared to the 1/2, which is the same thing as the square root. So first of all, we need to get this into the familiar form of every variable on one side, every variable on another side. So let's divide by the square root of 1 minus y squared. So x dy dx times 1 over the square root of 1 minus y squared, which just equals 1. There's nothing on the right side, but now we can multiply by dx and divide by x, which would give us dy, here I'll write this a little bit better, dy over the square root of 1 minus y squared equals 1 over x dx. So immediately, okay, every y is on the left, every x is on the right. That means it's separable, so that's nice. So as we've been doing, let's just take the integral of both sides. And so this integral right here, you might remember from Calc 2. This is one to just memorize. This is just arc sine of y. So arc sine of y equals the integral of 1 over x dx. That's just ln of x, and then plus c, constant of integration. And we want to solve for y. So we just take the sine of both sides, which would give us y equals sine of ln of x plus c, like that. And so that's it. We found y. All right, we'll go into another example here. Let's say we have one, maybe a bit more simple. We have dy dx equals y over x. All right, so all we got to do here is divide by y. So 1 over y times dy dx equals 1 over x, and then multiply both sides by dx. So now we have dy over y equals dx over x. And so, looks good. Every variable is alone on its own side. So now we take the integral of both sides. Integral of 1 over y is just ln of y. Integral of 1 over x is just ln of x. And I'll write the constant of integration here. And you notice I usually write it on the right, but you could write it on the left, it doesn't matter. So then we want to solve for y. So we're going to exponentiate both sides. So e to the ln of y equals e to the ln of x plus c. So this is going to give us y equals, because the e and the natural log always cancel each other out, this is going to give us e to the ln of x, and then I'm going to rewrite the plus c up top as e to the c. And that's because if you multiply exponentials, you add their exponents. And it's clear why I did this right in this next step, because e to the ln of x is just x. So here we have e to the c times x. And going back to the renaming, let's rename e to the c, which is just a constant, right? It's just a number. We have no idea what it is because we don't have any boundary conditions. So we can just rename it anything we want. Let's rename it c1, a new constant. So that means y equals c1x. Boom. Okay, so we'll just keep going with some more examples. So dy dx equals negative x over y. All right, first things first, I think you guys know what's up by now. We just got to get everything to be alone with its same variable on its own side. So multiply by y and multiply by dx. This will give us y dy equals negative x dx. And now let's take the integral of both sides. I'll leave the constant outside of the integral. So y squared over 2 equals negative x squared over 2 plus c. Multiply both sides by 2. We have y squared equals 2c minus x squared. But we can, of course, as we have been doing, rename 2c to be a new constant. 2c equals c1. So y then equals plus or minus the square root of c1 minus x squared. Like that. All right, there we go. That's going to be the final answer for y. And of course, if we wanted to, we could have solved for x, but in all of these examples, we are asked to solve for y. Okay, let's go into another example. So let's say dy dx equals 1 minus 2x, write that 2x y squared. Okay, so let's start by dividing both sides by y squared to get the dy and the y squared together. And then let's multiply by the dx to get the x and the dx together. 1 minus 2x times dx. Okay, so now we can just integrate both sides. Integral of 1 over y squared, well, that's the same thing as the integral of y to the negative 2. So this is going to be y to the negative 2 plus 1, negative 1, over negative 1, which equals x minus x squared plus c. Okay, so this is the same thing as saying negative 1 over y equals x minus x squared plus c. So I'll go ahead and put the negative on the other side in order to solve for y. 1 over y equals negative x plus x squared plus c1, where I'll define c1 as negative c, again, just so we have to write less. So then we take 1 over the left side and 1 over the right side. So 1 over y is just y. Take the 1 over everything. So this leaves us with x squared minus x plus c1. Okay, and that's going to be your answer for y. Okay, let's go into another example. X dx plus y e to the negative x dy equals 0. All right, so the y and the dx are already kind of split up. It's not dy over dx, but we notice that the dy sort of has an e to the negative x, which we don't want, so we have to separate the variables still. So first thing that I'll do is just write them in their own side, negative y, e to the negative x, dy. So then all I have to do here is divide by e to the negative x. So x dx e to the negative x equals negative y dy. All right, now 1 over e to the negative x is just e to the x. So x e to the x dx equals negative y dy. All right, so now we've done the separation part, we've done the ODE part really. So now Calc 2 knowledge comes in, we take integrals. All right, so on the left side, we have a integration by parts. So this is because we have a product of x and e to the x. And so little integration by parts tip here. The goal is to reduce the power of x so that we inevitably take an integral of just e to the x. You'll see what I mean. And so to reduce the power, we make u equals x, du equal 1, taking the derivative. Let's set dv equal to e to the x, and let's set v equals e to the x, just by taking the integral of this guy here. And so this still has a dx, and this still has a dx, like that. Okay, so now we employ the integration by parts formula, which says the integral of u dv, which we defined x and e to the x, dx, equals uv minus the integral of v du. Okay, so we'll just plug in what we know for the left side. So the integral of x e to the x dx is going to be x e to the x minus the integral v du. So this is just e to the x, and then du is just dx. All right, which still equals the right side of the integral of y dy. And so this is what I said earlier, by setting u equals x, we're reducing the order of x. So x to the first goes to x to the 0. X to the 0 is 1, so now we don't have to deal with another integration by parts. All right, so we can go ahead and just solve these integrals. X e to the x minus e to the x equals negative y squared over 2 plus c. Can't forget the constant of integration. Okay, so now we just have to go ahead and solve for y. So first off, I'll subtract c to the left side, which will give us it'll give us a negative c, but I'll define negative c as equal to c1. So negative y squared over 2 equals x e to the x minus e to the x minus c, but let's define minus c as c1. Okay, so now let's multiply both sides by a negative 2. So y squared equals negative 2 x e to the x plus 2 e to the x minus 2, c1. All right, and so again, there's really nowhere that this could end when it comes to renaming variables. We only do it to make life easier, to make the answer look better. So we can rename negative 2c1 to be c2, for example, which leaves us with y squared equals negative 2x e to the x plus 2e to the x plus c2. Okay, so then all we have to do is take the square root, and we have our answer. Pardon. Negative 2x e to the x plus 2e to the x plus c2. And that's going to be the answer. All right. Thank you everybody for watching. Hopefully you got something out of these explanations and these examples. Let me know if you have any specific questions and I'll be sure to answer them.